For basically all of human history, we've thought of aging as this absolute certainty, right? But what if that's about to change? In this explainer, we're going to dive into the science of aging and how it's being completely reframed, not as something we just have to endure, but as a problem that we can actually solve.
I mean, think about it. Since the dawn of time, aging has just been a fact of life. It was a one-way street, a guarantee. You're born, you live, you get old. It was just as certain as the sun coming up tomorrow. Something to be accepted, never something to be fought.
And the story was always the same, wasn't it? A slow, kind of inevitable process of just wearing down. A gradual buildup of damage that always led to frailty, to chronic disease, and, eventually the end. This was just seen as the unchangeable reality for everyone. What if that entire story is just wrong? What if we've been looking at the single greatest cause of human suffering through a completely wrong lens this whole time? Well, this is the very heart of a massive revolution that's happening in biology right now. There's this new field called geroscience, and it argues that the biological process of aging isn't some fixed law of nature. Nope, it's a modifiable process. And get this, by targeting aging itself, we can get at the root cause of pretty much every major chronic disease you can think of. So let's dig into this. This is a huge shift in thinking, right? We're moving away from this passive, it is what it is view, to a much more active, engineering-based approach to our own bodies. And this slide just lays it out perfectly. Look on the left, that's the old view. Aging is just what happens. It's totally separate from things like cancer or heart disease. But on the right, that's the new science. Aging is the master disease. It's the common driver, the root cause of all those other conditions. So if we can treat aging, we might just prevent all of them at once.
Okay, so how in the world do scientists even begin to tackle something as complicated as aging? Well, they start with a map. This is the hallmarks of aging. It gives researchers 12 distinct, measurable categories of damage. It basically turns the total chaos of aging into an organized set of targets we can actually aim at.
We can even simplify those 12 hallmarks into a really logical flow. So first, you've got the initial triggers, the molecular damage that kicks the whole thing off. Then, you've got the body's responses to that damage, which they work for a while, but eventually they start causing problems themselves. And finally, you get the result, total system failure, where our tissues just can't repair themselves anymore. Now, out of all of those, one of the most fascinating is something called cellular senescence. You gotta think of these as zombie cells. So a damaged cell stops dividing, which is actually good. It helps prevent cancer. But it doesn't die. It just hangs around like a zombie, pumping out this toxic soup of inflammatory signals that starts damaging all the healthy cells around it. And this slide shows the solution so well. On the left, you can see those zombie cells building up and spreading damage. But then a new class of drugs called senolytics comes in. They're like a special forces team designed to specifically hunt down and eliminate only the zombie cells. This clears out all that toxic inflammation and gives the healthy tissue room to regenerate. It's a hit-and-run strategy that is showing some incredible promise. And hey, this isn't just theory anymore. Let's see how this is translating into real-world medicine, because we now have the very first generation of drugs designed to fight aging that are already being tested in people. So check this out. We've got 3 leading strategies here. First up is metformin. It basically tricks the body into thinking it's in a state of caloric restriction, which forces cells to focus on repair and survival. The big trial for this, TAME, is huge because it's trying to prove that aging itself is a treatable condition. If they succeed, it could open the floodgates for all anti-aging drugs. Next is rapamycin, which is being tested to flip our cells from growth mode into repair mode. Super important for cleaning up cellular junk. And finally, senolytics, like that D plus Q combo, have already been shown by the Mayo Clinic to clear out those zombie cells in people. Okay, but slowing aging down is one thing. The next frontier, it's even more ambitious. Can we actually turn the clock back?
All right, this is where things get a little bit mind-bending. There's this technique called partial reprogramming. It uses a set of proteins, the Yamanaka factors, and the key word here is partial. It doesn't turn the cell into a blank slate stem cell. Instead, it just kind of wipes away all the chemical junk, the epigenetic noise that builds up on our DNA over time. It's literally like resetting your phone's software back to its original, fast, clean factory settings. And this quote just nails it. The goal isn't to erase what the cell is. It's just to restore it to a more youthful, better functioning version of itself. And this is the exact strategy that these heavily funded biotech companies, like Altos Labs, are chasing right now. Now, the biology of aging is just insanely complex, but we finally have a tool that's powerful enough to make sense of it all. Artificial intelligence is acting as the ultimate accelerator for this entire revolution. What you're looking at here is a powerful feedback loop. You've got AI sifting through just massive amounts of data, genomics, protein folding, you name it, to find new targets for aging. Then, it designs completely new drugs to hit those targets. They test the drugs, feed the results back into the AI, and the whole cycle repeats, getting smarter each time. This is shrinking drug discovery from a decade-long process down to a matter of months. It's incredible. But there's a big problem. If you're testing an anti-aging drug, you can't exactly wait 30 years to see if it worked, right? You need a better way to measure aging than just counting someone's birthdays. You need to be able to measure biological age. And that is where aging clocks come in. This chart shows just how far they've come. The first generation clocks, they were pretty good at predicting your chronological age. But look at that jump to the third generation, to clocks like Grim Age. They are so much better because they're trained on actual mortality data. This makes them incredibly powerful at predicting your real health span and your risk of disease. And for testing new therapies, this is a total game changer. And let me be clear, this isn't just science fiction happening in some university basement anymore. A whole ecosystem of really well-funded companies has popped up to move this science from the lab into the clinic. You have Altos Labs with billions of dollars focused on reprogramming, and companies like In Silico Medicine that already have AI-designed drugs in phase 2 trials. This science is quickly becoming a serious, massive industry. So as you can see, the science is just moving at a breathtaking pace. But this takes us from the how to the what if. And it brings up what might be humanity's next great question. And here you see the two sides of that coin. On the one hand, you have the longevity dividend. If we can extend our health span, people stay healthy and productive for way longer, which could save trillions in healthcare. But on the other hand, there's the terrifying risk of a longevity divide. What if these therapies are super expensive? Could we create a world where the rich get to live for centuries while everybody else doesn't? A biological caste system? The science is pretty clear. The question is no longer if we can intervene in aging, but how we're going to do it. And honestly, how we answer that question is going to define the entire future of our species.